Dysprosium is a chemical element with the symbol Dy and atomic number 66. It is a rare earth element with a metallic silver luster. Dysprosium is never found in nature as a free element, though it is found in various minerals, such as xenotime. Naturally occurring dysprosium is composed of 7 isotopes, the most abundant of which is 164 Dy. Dysprosium was first identified in 1886 by Paul-Émile Elie de Bois-Baudran, but was not isolated in pure form until the development of ion exchange techniques in the 1950s. Dysprosium is used for its high thermal neutron absorption cross-section in making control rods in nuclear reactors, for its high magnetic susceptibility in data storage applications, and as a component of terphenyl D. Soluble dysprosium salts are mildly toxic, while the insoluble salts are considered non-toxic. Characteristics. Physical properties. Dysprosium is a rare earth element that has a metallic, bright silver luster. It is soft enough to be cut with a knife, and can be machined without sparking if overheating is avoided. Dysprosium's physical characteristics can be greatly affected by even small amounts of impurities. Dysprosium and holmium have the highest magnetic strengths of the elements, especially at low temperatures. Dysprosium has a simple ferromagnetic ordering at temperatures below 85 K. Above 85 K, it turns into an helical antiferromagnetic state in which all of the atomic moments in a particular basal plane layer are parallel, and oriented at a fixed angle to the moments of adjacent layers. This unusual antiferromagnetism transforms into a disordered state at 179 K. Chemical properties. Dysprosium metal tarnishes slowly in air and burns readily to form dysprosium oxide. 4 Dy plus 3022 Dy2O3. Dysprosium is quite electropositive and reacts slowly with cold water to form dysprosium hydroxide. 2 Dy plus 6H2O2 Dy3 plus 3H2. Dysprosium metal vigorously reacts with all the halogens at above 200 degrees Celsius. 2 Dy plus 3F22 DyF3. 2 Dy plus 3Cl22 DyCl3. 2 Dy plus 3Br22 DyBr3. 2 Dy plus 3I22 DyI3. Dysprosium dissolves readily in dilute sulfuric acid to form solutions containing the yellow Dy ions, which exist as a 3+ complex. 2 Dy plus 3H2SO4. 2 Dy3 plus 3SO2 minus 4 plus 3H2 to the resulting compound. Dysprosium sulfate is noticeably paramagnetic. Compounds. Dysprosium halides, such as DyF3 and DyBr3, tend to take on a yellow color. Dysprosium oxide, also known as dysprosia, is a white powder that is highly magnetic, more so than iron oxide. Dysprosium combines with various nonmetals at high temperatures to form binary compounds with varying composition and oxidation states +3 and sometimes +2, such as DYN, DYP, DYH2 and DYH3, DYS, DYS2, DY2S3 and DY5S7, DYB2, DYB4, DYB6 and DYB12, as well as DY3C and DY2C3. Dysprosium carbonate, Dy23, and dysprosium sulfate, Dy23, result from similar reactions. Most dysprosium compounds are soluble in water, though dysprosium carbonate tetrahydrate 3,4-hydrogen oxide and dysprosium oxalate decahydrate 3,10-hydrogen oxide are both insoluble in water. Two of the most abundant dysprosium dysprosium carbonates, tangleride 3,2,3 hydrogen oxide and kazooate, are known to form via a poorly ordered precursor phase with a formula of dy23,4H2O. This amorphous precursor consists of highly hydrated spherical nanoparticles of 10 to 20 nanometers diameter that are exceptionally stable under dry treatment, at ambient and high temperatures. Isotopes. Naturally occurring dysprosium is composed of 7 isotopes: 156 dy, 158 dy, 160 dy, 161 dy, 162 dy, 163 dy, and 164 dy. These are all considered stable, although 156 dy decays by alpha decay with a half-life of over 1 times 1018 years. Of the naturally occurring isotopes, 164 dy is the most abundant at 28%, followed by 162 dy at 26%. The least abundant is 156 dy at 0.06%. 29 radioisotopes have also been synthesized, ranging in atomic mass from 138 to 173. The most stable of these is 154 dy, with a half-life of approximately 3 times 106 years, followed by 159 dym with a half-life of 144.4 days. The least stable is 138 dy, with a half-life of 200 ms. As a general rule, isotopes that are lighter than the stable isotopes tend to decay primarily by beta plus decay, while those that are heavier tend to decay by beta minus decay. However, 154 dy decays primarily by alpha decay, and 152 dy and 159 dy decay primarily by electron capture. Dysprosium also has at least 11 metastable isomers, ranging in atomic mass from 140 to 165. The most stable of these is 165 mdy, which has a half-life of 1.257 minutes. 149 dy has 2 metastable isomers, the second of which, 149 square meters dy, has a half-life of 28 nanoseconds. History. In 1878, erbium ores were found to contain the oxides of holmium and thulium. French chemist Paul-Émile Lecoq de Bois-Baldrin, while working with holmium oxide, separated dysprosium oxide from it in Paris in 1886. His procedure for isolating the dysprosium involved dissolving dysprosium oxide in acid, then adding ammonia to precipitate the hydroxide. He was only able to isolate dysprosium from its oxide after more than 30 attempts at his procedure. On succeeding, he named the element dysprosium from the Greek dysprositos, meaning hard to get. The element was not isolated in relatively pure form until after the development of ion exchange techniques by Frank Spedding at Iowa State University in the early 1950s. In 1950, Glenn T. Seaborg, Albert Guerso, and Stanley G. Thompson bombarded 241 with helium ions, which produced atoms with an atomic number of 97 and which closely resembled the neighboring lanthanide terbium. Because terbium was named after it, the city in which it and several other elements were discovered. This new element was named berkelium for the city in which it was synthesized. However, when the research team synthesized element 98, they could not think of a good analogy for dysprosium, and instead named the element californium in honor of the state in which it was synthesized, California. The research team went on to point out that, in recognition of the fact that dysprosium is named on the basis of a Greek word meaning difficult to get at, that the searches for another element a century ago found it difficult to get to California occurrence. While dysprosium is never encountered as a free element, it is found in many minerals, including xenotime, fergusonite, gadolinite, exonite, polycrase, blomstrandine, monazite and bastnasite, often with erbium and holmium or other rare earth elements. Currently, most dysprosium is being obtained from the ion adsorption clay ores of southern China, and future sources will include the Halls Creek region in Western Australia. In the high yttrium version of these, dysprosium happens to be the most abundant of the heavy lanthanides, comprising up to 7 to 8% of the concentrate. The concentration of Dy in the Earth's crust is about 5.2 mg per kilogram and in seawater 0.9 nanograms L. Production. Dysprosium is obtained primarily from monazite sand, a mixture of various phosphates. The metal is obtained as a byproduct in the commercial extraction of yttrium. In isolating dysprosium, most of the unwanted metals can be removed magnetically by a flotation process. Dysprosium can then be separated from other rare earth metals by an ion exchange displacement process. The resulting dysprosium ions can then react with either fluorine or chlorine to form dysprosium fluoride, DyF3, or dysprosium chloride, DyCl3. These compounds can be reduced using either calcium or lithium metals in the following reactions: 3Li plus DyCl3 Dy plus 3 lithium chloride. The components are placed in a tantalum crucible and fired in a helium atmosphere. As the reaction progresses, the resulting halide compounds and molten dysprosium separate due to differences in density. When the mixture cools, the dysprosium can be cut away from the impurities. About 100 tons of dysprosium are produced worldwide each year, with 99% of the total produced in China. Dysprosium prices have climbed nearly 20-fold, from $7 per pound in 2003 to $130 a pound in late 2010. The price increased to $1,400 per kilogram in 2011 but fell to $240 in 2015, largely due to illegal production in China which circumvented government restrictions. According to the United States Department of Energy, the wide range of its current and projected uses, together with the lack of any immediately suitable replacement, makes dysprosium the single most critical element for emerging clean energy technologies. Even the most conservative projections predict a shortfall of dysprosium before 2015. As of late 2015, there is a nascent rare earth extraction industry in Australia. Applications. There are not many applications unique to dysprosium. Theodore Gray wrote in his book The Elements, a visual exploration of every known atom in the universe. Look up dysprosium, and you have to go to the 4th page of results before finding anything that isn't a periodic table website's entry for dysprosium. Usually an obligatory, it's an element, so we have to have a page about it sort of page. Dysprosium is used in conjunction with vanadium and other elements in making laser materials and commercial lighting. Because of dysprosium's high thermal neutron absorption cross-section, dysprosium oxide nickel cermets are used in neutron-absorbing control rods in nuclear reactors. Dysprosium cadmium chalcogenides are sources of infrared radiation, which is useful for studying chemical reactions. Because dysprosium and its compounds are highly susceptible to magnetization, they are employed in various data storage applications, such as in hard disks. Dysprosium is increasingly in demand for the permanent magnets used in electric car motors and wind turbine generators. Neodymium-ion boron magnets can have up to 6% of the neodymium substituted by dysprosium to raise the coercivity for demanding applications, such as drive motors for electric vehicles and generators for wind turbines. This substitution would require up to 100 grams of dysprosium per electric car produced, based on Toyota's projected 2 million units per year. The use of dysprosium in applications such as this would quickly exhaust its available supply. The dysprosium substitution may also be useful in other applications because it improved the corrosion resistance of the magnets. Dysprosium is one of the components of terphenyl-D, along with iron and terbium. Terphenyl-D has the highest room temperature magnet restriction of any known material, which is employed in transducers, wideband mechanical resonators, and high-precision liquid fuel injectors. Dysprosium is used in dosimeters for measuring ionizing radiation. Crystals of calcium sulfate or calcium fluoride are doped with dysprosium. When these crystals are exposed to radiation, the dysprosium atoms become excited and luminescent. The luminescence can be measured to determine the degree of exposure to which the dosimeter has been subjected. Nanofibers of dysprosium compounds have high strength and a large surface area. Therefore, they can be used to reinforce other materials and act as a catalyst. Fibers of dysprosium oxide fluoride can be produced by heating an aqueous solution of DYBr3 and sodium fluoride to 450 degrees Celsius at 450 bars for 17 hours. This material is remarkably robust, surviving over 100 hours in various aqueous solutions at temperatures exceeding 400 degrees Celsius without redissolving or aggregating. Dysprosium iodide and dysprosium bromide are used in high-intensity metal halide lamps. These compounds dissociate near the hot center of the lamp, releasing isolated dysprosium atoms. The latter re-emit light in the green and red part of the spectrum, thereby effectively producing bright light. Several paramagnetic crystal salts of dysprosium are used in adiabatic demagnetization refrigerators. Precautions. Like many powders, dysprosium powder may present an explosion hazard when mixed with air and when an ignition source is present. Thin foils of the substance can also be ignited by sparks or by static electricity. Dysprosium fires cannot be put out by water. It can react with water to produce flammable hydrogen gas. Dysprosium chloride fires, however, can be extinguished with water, while dysprosium fluoride and dysprosium oxide are non-flammable. Dysprosium nitrate, Dy3, is a strong oxidizing agent and will readily ignite on contact with organic substances. Soluble dysprosium salts, such as dysprosium chloride and dysprosium nitrate, are mildly toxic when ingested. Based on the toxicity of dysprosium chloride to mice, it is estimated that the ingestion of 500 grams or more could be fatal to a human. The insoluble salts, however, are non-toxic.